Hello, statisticians. Back here with normal distribution part 2, which is standardizing an observation. So in part 1, talked a little bit about various density curves and how they can have many different shapes, but focused a little more on the normal curve, which again was the bell curve. Oops. So that curve there. So we're going to dig into that curve a little more, and a little more with unique values that you could come across. So the first thing we're going to look at here is standardizing an observation. So in any population, there would be a certain population mean that we call mu, and then a population standard deviation that we call sigma. And this would be something that would have to be given to us because it would have to be population data. So it's not something we'd collect. It's not something that we'd find, put into our list and run one variable stats on. That's typically samples that we put in there. This would be something where the question says, for instance, the mean ACT score at Minnetonka High School is 27. And the standard deviation is 3. And so then what we would do is we would take in this formula here is we would take individual ACT scores as x. Okay, so for instance, if your score was a 32, then what you would be doing here is 32 minus the mean of 27 divided by 3, which is 5/3 or about 1.67, which means that your ACT score would then be about 1.67 standard deviations above the mean. So that's what the z-score is representing. So a z-score in general is a standardized value, and what it is doing again is calculating the number of standard deviations a value is from the mean. And if you recall from last lesson, in a normal curve, again the center is 0 standard deviations from the mean. 1 and -1 are at what's called the inflection point, so where it goes from steeper to not as steep here. That would be 1 standard deviation above and 1 standard deviation below, and about 68% of the values are within that range. -2 to 2, so that would be your 2 standard deviations from the mean, or above or below, and that is the middle 95%. So 95% of a population is within 2 standard deviations of whatever the mean is: mean height, mean IQ, mean distance, mean ACT score, whatever it happens to be. And then we have 3 standard deviations from the mean, which would be the middle 99.7% of values. And so almost everybody is within 3 standard deviations of the mean in a population, with about 0.15% roughly on each side that are more than 3 standard deviations from the mean. So that would be, in professional sports, the people up here would be the best in the league. And maybe amongst the best ever if they're above 3 standard deviations above the mean. So that's this idea of standardizing, is converting from a typical scale, which in this case, the ACT problem, the typical scale would have been centered at 27, and with a standard deviation of 3 would look like this. So it would look with this scale here, and would go down. This would be 24. 21 and 18. So that's the ACT scale here. Sorry, running out of space there. And this is the Z scale. Okay, and so they are synonymous. They go hand in hand, but one of them is, of course, the actual values, and one of them is in terms of the number of standard deviations from the mean. So it's like we're converting units. It's almost as though we're switching inches to centimeters. But what happens is that -3 to 3 scale works for any normal population. Whereas the actual scale here, the ACT, of course, would be centered at 27, whereas heights might be centered at 68, and SATs are centered in the hundreds and so forth. But that Z scale is constant for all of these populations, running from -3 to 3 with just a little bit outside of each of those. And that is why it's called the standard normal, because it has a standard set scale here of this -3 to 3. So that's the standard normal. So all z-scores are falling on this curve. This is considered normal with a mean of 0 and a standard deviation of 1. And from there we find out what proportion of the curve is below, above, or between points. So So the types of problems we will encounter here are going to be really one of three types of problems if we're looking at probabilities around the curve. Is it could be a scenario where we're looking at what percent is less than a value, what percent is greater than a value, whatever it happens to be, or what percent is between two values. Sorry, that's a pretty ugly normal curve there, but what percent is between those two values. And just to note here, the idea of being greater than versus greater than or equal to doesn't really matter in this situation because there are an infinite number of vertical lines that you could put in this normal curve. And so the idea of having a z greater than 2 or greater than or equal to 2 makes really no difference. It's going to be the same answer either way, so it doesn't really matter which one of those two you include. Now with the idea of the values of standardized score, what it allows us to do is a couple things here. We can compare values from different populations. So for instance, if you took the ACT and the SAT, you could figure out which score was actually better based on which one had the higher z-score. Or if you golfed on two different golf courses that had a different par number, you could figure out which round was better by which one had the lower z-score, by which one was more under the proportionally under par, not just saying 6 under par and 6 under par, which technically has a slightly different meaning if it's 72 or 71, statistically speaking. Allows us to determine percentile, again, which is the percent of the population we are tied or better than. And it allows us to work backwards. So if we figure out what percentile, if we're given what percentile we were, for instance, you scored in the top 10% on your ACT, you can work backward to find the X value from that, the original value. So here it is, the two biggies, and we had some formatting issues here, but the two big types of problems that you will encounter will be a raw value to percentile. So you have this ACT score, what percentile were you? In other words, again, what percent of the whole population of ACT takers, or you could switch it to Minnetonka ACT takers or whatever, what percent of people were you tied or better than? Or again, we could use going from percentile back to the raw value. In other words, you scored in the top 10% on the ACT. What was your ACT score? And we could work backward. Now, the two processes here, when you are going from raw value to percent, what you are going to do is you start off with an X, and then you input it into the formula. Excuse me. Input it into the formula to get a z-score, and then you use that z-score to get a percentile. Okay? So what you're doing here in this part is a function on your calculator that's under second vars, and it's normal CDF. Okay, second vars, normal CDF. And what our calculator has is when we go with the z-score, we put in the lower bound, upper bound, 0, and 1. So again, if the scenario is a less than, your lower bound is technically negative infinity. But I would just put in like a negative 99 up to your z-score, which this z-score maybe is negative 1.22 or something like that. So that would be 1.22. And then the mu and the sigma would be 0 and 1 because we're converting to a z. That's a little different if you've taken FST. That allows a little shortcut to put in the actual mean and standard deviation of this problem. We always use 0 and 1 because we have to find the z-score. Now, if it were a greater than scenario, okay, so it were, say, from here and up, then that might be 2.01 as your lower bound to 99 as your upper bound because we keep going up on that one, okay? And then finally, if it's a between scenario, your lower and upper bound are just the two z-scores that you have to find, because there would be two z-scores since it's finding, for instance, from, let's use the same curve, but finding from here to here, you would have a z-score here and a z-score here, and this, of course, would be your lower bound, and then this would be your upper bound on the right. And then that answer will be what percent is the probability of falling in that area. So for instance, if you were to put in the normal CDF from negative 99 to negative 1.22 as we had in the red example here, that gives you an answer of 0.1112. So there would be an 11.12% chance, and you can check this yourself right now if you want, but there'd be an 11.12% chance that you'd have a z-score of less than or equal to negative 1.22. Similarly, if you were to do the other end of this on the 2.01 to 99, that would be a probability there of 0.0222, and so it's a 2.22% chance that you're up in that area. Again, the total area of the whole curve again is 1, so it's just a portion of 1 that we're looking at because it's a density curve. So there's a 2.22% chance that you are 2.01 standard deviations above the mean or higher. And then this here, the black one, again, you'd put in the 2 z-scores and find a percent there as well. But you can convert these, you can leave them as decimals or convert them to percents, and that is, again, the likelihood of being in that area. So this problem might be the chances that you have an ACT of 34 or higher or something like that. Okay, so now moving on to the second one here, the percentile to raw values. So here's how this one would work. This one isn't so much about shading as it is about saying, okay, let's say your ACT is in the top 10%. So your ACT is right here. Okay. Now, what we are going to use here is we're starting from a percentile, and then we're going to go to the Z and back to the X. And you can notice, or you can see here, that that's exactly the opposite of what we did there. So what you're going to do to go from a percentile to a Z is use the inverse norm function on your calculator, which is under second vars. So I go to second vars, and I'm going to go to inverse norm. Now what inverse norm wants is the area to the left. Okay, so if I'm in the top 10%, I would actually read that as being in the 90th percentile. Okay, and again, you can check this, but the 90th percentile is actually a z-score of 1.28. It's not that far above the mean, actually, to be in the 90th percentile. So 1.28 is your z-score. Okay, so now to get from your z-score back to x, it's just algebra. Okay, if we have again, using this formula, we now have a z-score of 1.28. We're trying to find x. Again, from our last slide, the mean we said was 27 and the standard deviation was 3. Multiply by 3 on both sides, add the 27, and that would give you your actual ACT, which in this case would be an ACT of about 30.8 or about 31. And so that's how you would find the x given the percentile. And again, if it said bottom 10%, then your inverse norm is just 0.10. And that would actually be negative 1.28. Okay, because this curve is symmetric. So if it were the bottom 10% here, you're at the 10th percentile, that would actually be negative 1.28. And then your ACT, instead of being 3.8 above the mean, would now be 3.8 below the mean. And so you'd have an ACT of about 23.2 actually in this case. So that's the calculations there. Now, a couple things that you're going to see is it's called a probability statement. Okay, so a probability statement here is the idea of being able to write, in this case, what's the probability that x is greater than 169.5, okay? Which might be the equivalent of saying, what's the probability that z is greater than 2, okay? And so what that suggests is that we're in some scenario here where the z-score is 2, but the actual raw value is 169.5, and it wants greater than that, okay? So that's a probability statement. You should be able to write at least this probability statement with the z. And then you would calculate the z-score from there, which again would be a normal CDF, lower bound of 2, upper bound of 99, and that would give us an answer here of about 0.0228, okay, or 2.28% chance. But that's the process there. So you've got a probability statement. You may have to calculate the z-score, and then you use the normal CDF function. Okay, obviously this one already had the z-score here, but if you didn't have it, you'd have to calculate the z-score before using that normal CDF. So there's that process a little more deeply. Now here's just a couple of examples. Okay, if 18 to 24 year old women have a mean height of 64.5, so that means mu is 64.5, and we know it's mu, not x bar, because it's all women. Okay, if it said a sample of 30 women, then it would be x bar. But because it's the population, then it's mean, or then it's mu, sorry. And then a standard deviation of about 2.5. And it wants us to standardize the heights for 60 and 68-inch women. So if in that situation, that would be a z equals 60 minus 64.5. Again, we're using this formula now. Divided by 2.5. Sorry, that's 64. And so we would then have a z-score there of negative 1.8. So that woman is 1.8 standard deviations below the mean. And then the 68-inch woman would be 68 minus 64.5 over 2.5. And so in that case, we would have a z-score there of 1.4. And so that individual would have would be 1.4 standard deviations above the mean in terms of her height. And again, on a normal curve, it's always centered at 0. Negative 1.8 would be over here, and 1.4 would be over here. And then again, it might ask, what's the probability that we're taller or shorter than 68 inches, or taller or shorter than 60 inches? Could go either direction. Or it might ask, what's the probability that we are between 60 and 68 inches, in which case it's all of this is between 60 and 68 inches, which, as you can see, is a majority of women between 5 feet and 5'8". Example 2 here, what proportion of women are less than 68 inches using that same mean and standard deviation? And so in this situation here, we look at, again, it's asking what's the probability that x is less than 68. So we're going to find that z-score. And again, just pay attention to my notation here. So again, that gives us a z-score of 1.4. Okay, that's the x minus mu over sigma there. And so this is equal to the probability that z is less than 1.4. So you don't need to write both of these statements, but you should be able to write one of them. And it's probably easier to just always write the standardized value. Now, the reason you need to write one of them is here comes our answer right here. And if I just write that answer in space, then it has no context of where it comes from. So what we're doing is we're showing, in this case, this answer here is 0.9192. Okay, and so if we just write 0.9192 with nothing else around it, we don't give it any context of where that answer comes from. So what we're doing here is showing that 0.9192 is the probability that somebody has a z-score of less than 1.4, or the probability that they have a height of less than 68. So you're just giving it context there, being able to write that statement. The z calculation can be on its own down here, but your answer should have a probability statement with it. So in other words, 91.92% of women, or about 92% of women, are shorter than 5'8", according to this model. Example 3 now is a between scenario. So in this case, for distribution of blood cholesterol for 14-year-old boys is roughly normal, okay, which again just means it follows the bell curve, with a mu of 170 and a sigma of 30. And the question it's now asking is, what's the probability that we have an x between 170 and 240? So we naturally need to find two z-scores here. Well, the first z-score is pretty easy. because it's 170, which is right at the mean, so that's right at dead center at 0, which is 170. The second z-score here is 70 over 30, or 2.33, so that's technically approximately. So we are trying to find here the probability that 0 is less than z, which is less than 2.33, which again is just converting your values to the z-scores, okay, which on the curve up here looks like this. So we're trying to find this area here, okay? And so we again go back to second VAR's normal CDF, and you don't need to write second VAR's normal CDF. You just need to get the answer as long as you've written the probability statement, and that is approximately 0.4901. Which is, as you can see, most everything from the mean up, minus that just top 1% there that we don't have right there. But so 49.01% of 14-year-old males have a blood cholesterol between 170 and 240 milligrams per deciliter. And so that's our value there. Again, you could write that as 49.01% if you want to, but you should have at least that or this statement, and then you have your calculations over here. And with your calculations, make sure you actually solve them. Okay, so make sure you actually write what this answer is here and here, rather than just writing the formulas themselves. Finally, that was that going from proportions back to z's. So this is, again, question's going to give a percent above or below a certain point. So you're at the 80th percentile, or you're in the top 20% or something like that. You're going to use that inverse norm again, and then use that z-score to solve back to the x. So just an example of that here quickly. If I'm in the top 10% of ACTs, and the ACTs follow a normal model with a mean of 23 and a sigma of 3, that's what that notation suggests. So now I'm in the top 10%. So that just means this is 0.10 and this is 0.90. We are trying to solve the z that goes there and ultimately the x that goes there. Okay, so the first thing I'm going to do, so actually the way this would be written is probability that our value is, we're trying to find this number here, is 0.10, which is also the same as saying the chance that we're less than that value is 0.90, which you don't need to write, but that's just a follow-up there. So we're going to inverse norm here. So we're just going to say the 90th percentile is, and I'll put an arrow there, the 90th percentile is a z-score of 1.28. And now we take that 1.28 and we put it in our formula. So 1.28 equals x minus mu, which was 23, over sigma, which was 3. And we perform a little algebra here, and that would tell us that the ACT here would have to be about 26.84, or roughly an ACT of 27. But you can just leave it at 26.84. No need to round right now on that. So that would just be going the other direction from percentile back to x. Here are some links that you can go look at in terms of the business uses of standard deviation and z-scores and the normal curve and things like that. And finally, there's also this idea of an investment example of, would you rather have the small standard deviation, the medium, or the big? And this again is an argument that could be had amongst folks that folks closer to retirement probably prefer scenario 1. Folks who are younger and have more time to wait out the market would probably prefer scenario 3. But I won't get into this here, but we could get into the normal curve for each of those, as investments oftentimes follow a normal curve. And we could look at that kind of, this would be the aggressive play, the intermediate play, and the conservative play when it comes to investing. And again, a lot of things with investing follow that normal curve. So I think I'll just leave it at that right there. And if you have any questions, as always, please ask. And thanks for watching and listening.